Last time we were discussing about functions, simple functions h, z, where only zeros were present, that is only the numerator polynomial was there. Now, let us take the second case when only poles are present. That means only the denominator polynomial is present, numerator is 1. Suppose there is a pole here. Okay. So, h z is appearing as 1 minus some, okay, I will call it r again, r e to the power, okay, r z minus 1, r is less than 1. Then h e to the power j omega squared will be, once again you can break it up, z is equal to e to the power j omega. Okay. So, how much is it? 2 r cos omega, all right, 1 minus r e to the power j omega magnitude squared is 1 minus r cosine omega whole squared plus r square, all right. So, 2 r cos omega plus r square under root of this will give me h magnitude. So, as we are going along this, when it is coming to 0, omega equal to 0, this distance is minimum, all right. So, the distance is minimum, that means the function is maximum at that frequency. It is having maximum value here, and when it is going to pi, this distance is maximum. So, this becomes, overall function becomes minimum. So, at pi it is falling like this. It may fall like this, but it is starting from maximum going to minimum. We will see the nature of variation later on, and again it will be going like this. So, this is a high pass or L pass? Low pass. So, a 0 here on the real axis gives me a particular factor corresponding to that gives me a high pass. A pole on the real axis, positive real axis, gives me a low pass. Now, if a pole goes to this side, then the distance is maximum here. So, then it becomes a high pass, and reverse is the case in case of zeros. We did not mention earlier, 0 coming to this side will give you low pass. If I have a pair of poles, once again say somewhere here and here, if I have a pair of poles, okay, before we take it up, suppose there is a pole on the real axis. If there is a pole here itself, then the function is 1 minus z inverse, z is equal to 1, all right. So, this is 1 by 1 minus e to the power minus j omega. When omega is equal to 0, how much is it? Infinity. Okay. So, it will be, and omega is equal to pi, means it becomes plus 1, the half. It will be like this. So, this is 2 pi, this is pi, all right. This will tend to infinity. Now, this type of filter function we do not like. Why? You give an impulse, what is the response? What is the impulse response of this? It will be 1, 1, 1 1. This is basically inverse of a unit step. So, by giving an input, if I give a delta input, if I get an output as unit step, what is it? What is it? It is an accumulator or integrator, alright. So, we do not want an integrator as such. There may be very specific requirements in some situation where you require an accumulator. So, the output will be all ones. Anyway, let us get back to the original problem. So, 1 by e to the power minus j omega, it will have a characteristic like, what is it like? If I have a pole on the positive real axis inside the unit circle, somewhere here that we have seen. Now, we are having a pole here. So, as we keep on changing the frequency, somewhere around this point, when it is equal to theta, the distance is minimum, that means the function becomes maximum, alright. So, it becomes a function like this, just reverse of the situation that you had in case of zeros. When omega is exactly equal to theta, we get a function like this, alright. Now, next, this is a general case when you have both poles and zeros. We are considering for the time being first order functions. Hz equal to 1 plus z inverse by 1 minus r z inverse into some constant k. Now, this r is necessarily less than 1 because we want this to be inside, poles must be inside. So, the denominator must not have the roots outside the unit circle. Numerator can have anywhere. So, we have chosen a very simple function, the 0 is at minus 1. So, then the system becomes, yes, why can't the pole lie outside the unit circle? Okay, let us have that is a very good question. Suppose we have 1 minus 5 into z inverse. What will be the z transform, inverse z transform? 5 to the power n un. Inverse means it is a impulse response. So, impulse response is unbounded. Okay. So, it is an unstable system. So, we do not want poles to be located outside the unit circle. Now, this is the function. What would be h e to the power j omega? It will be k into 1 plus e to the power minus j omega divided by 1 minus r e to the power minus j omega magnitude. So, simplify this, it is h squared is k squared into, if you square it up, you will get 1 plus cosine omega, we saw earlier, it is 1 plus cosine omega squared, okay, 1 plus 2 plus 2 cos omega gives me at, okay. Is this all right? Okay. And then 1 plus r square minus 2r cosine omega. Am I all right? Now, suppose at omega equal to 0, what is it? At omega equal to 0, this is maximum? Is not. This is subtracting maximum portion from the denominator. So, the denominator is reducing and this is becoming maximum. So, this function is maximum here, all right. So, if I normalize it with respect to the maximum value, that is at omega equal to 0, then h, I take h at omega equal to 0 to be 1. Then what should be the value of k? that means k square into at omega equal to 0, this is 4 by 1 plus r square minus twice r, so 1 minus r whole square, that should be equal to 1, or k equal to 1 minus r by 2. Okay. So, I will take h z in a normalized form as 1 minus r by 2 into 1 plus z inverse by 1 minus r z inverse. Okay. I have just normalized with the maximum value, with respect to the maximum value. So, h e to the power j omega you can write in the standard form. What is that frequency? What is that frequency at which power is half, that is the half power frequency, or in terms of dB it is 3 dB. What is the frequency omega c at 3 dB, that is, or I call it half power frequency. It is maximum at omega equal to 0, cosine omega half, some people write omega half, some people write omega c. Okay. This is more specific at half power, that is 3 dB point. Now, can you find out the numerator should be half the denominator, then only it is h square. Okay. So, h squared we saw is 1 minus r by 2 whole squared, this is k squared, into 1 plus cosine omega whole squared 1 plus z inverse plus sine omega squared divided by 1 minus r cosine omega squared plus r sine omega squared, and this must be equal to half at that frequency. So, from there if you just square it up and then see, equate, you will get 1 minus r whole squared into 1 plus cosine omega, there will be a term 2 squared, so that will be 4, so that will be getting cancelled with this, is equal to 1 plus r squared minus 2r cosine omega. Are you getting this? Therefore, cosine omega half, solution of this is cosine omega half is 2r by 1 plus r square, or r you can write as 1 minus sine omega half by cosine omega half. So, if you are given the half power frequency, that is something like a cutoff frequency, okay, you can design the filter, you can select a particular value of r, or given r you can determine what it will be its half power frequency. This is a first order model for the filter, that is both the numerator and denominator are of power z to the power minus 1. Now, any hz I can always write as, say, you can factorize the numerator, factorize the denominator. So, h1z into h2z into so on. So, they will be all in cascade. So, some may be low pass, some may be high pass, and so on. So, it is a net product of all these characteristics that will be determining the overall characteristics of the function. So, I can have, say, a low pass. For example, somebody may have a low pass filter like this, all the frequencies are allowed up to a frequency say omega 1, after that it tapers off, alright. It is, suppose this is a half power frequency, and another one h2, as like this, omega 2. Omega 2 is greater than omega 1, much greater than omega 1. Then what will be the combination? Here it is high, but here it is low, the product is very low. High means 1, okay, normalized. Then it will start from a low value. Somewhere in the middle it will be two finite products. Again here it is high, but this is low, so it will be somewhat like this, it will be a band pass. Suppose omega 1 is less than omega 2, omega 1 is greater than omega 2, okay, will it be same? Shifted. So you keep on changing this, alright, you can keep on changing this. If I have two low pass filters, one is like this, the other one is like this, then the product will be, you see at this edge it is a very small quantity, this is also falling very fast, so the overall product will be falling faster. So you can get sharper filters, alright. So if you want to have a very sharp cutoff, alright, almost tending to an ideal one, then you can have 2 or 3 such low pass filters in cascade, alright. I can have the same filter function, square it, so H1 squared, H1 into H1 into H1, if I put the same H1, I will get the same filter function, but with much sharper fall, okay. So the roll off can be adjusted by having the filter order increased, okay. Now if in the same function we have say H high pass is k into 1 minus z inverse by 1 minus alpha z inverse. The last one that we had, if you remember, 1 plus z inverse. Now I am shifting the 0 to the other side, this I have retained as it is. Then what do you get? Just like the previous case of only zeros, now I put a 0 here, earlier it was earlier the 0 was here, now I have put a 0 here, okay. So now z is equal to 1 is a 0 and there is a pole here. So in the first case it was like this, in the second case it is like this. At omega equal to 0, now this is minimum 0, so it will start from 0, will go on like this. So this is a high pass characteristics. The earlier one was falling. Here also you can determine, I leave it as an exercise, find out the half power frequency, omega half. All right. Now let us take some interesting distribution of the filter coefficients. Suppose we have a symmetric distribution, okay. H n is a finite length, that is only the numerator again, only the zeros, which is H0, H1, H2, H3, H2, H1, H0. That means suppose H0 is this much, H0, H1, H2, H3, then again H2, that means H4 is H2, H5 is H1, then H0. How many points are there? 1, 2, 3, 4, 5, 6, 7. So, number of points n is odd. Okay. We are starting with an odd sequence, odd number of points, and it is symmetric about the middle point. What will be h e to the power j omega like? It will be h0 plus h1 e to the power minus j omega and so on. Last term is 1, 2, 3, 4, 5, 6, h0 e to the power minus j 6 omega. Sorry. Is that all right? Now, I can pair these two terms, write them together, put them under the same bracket, plus h1 plus h1 into e to the power minus j omega, h1 into e to the power minus j omega plus h1 into e to the power minus j 5 omega. Is that all right? Plus h2 e to the power minus j, how much? 2 omega plus h2 e to the power minus j 4 omega. Okay. Plus h3 e to the power minus j 3 omega. All right. Now, you add these two together. You can take the common term out, h0, and if I take the mid value, this is e to the power j 0. So, 0 and 6 omega, what is the average? 3 omega. So, I will take e to the power minus j 3 omega outside. So, it will be h0 into e to the power minus j 3 omega outside. Okay. Inside I will be left with e to the power plus j 3 omega, e to the power minus j 3 omega. Okay. So, it will be twice cosine 3 omega. Is that okay? Similarly, second term, could you suggest how much it will be? E to the power minus j omega, if I take common, j 3 omega, is it not? Because it is the average of 5 and 1 that I am taking out. Okay. So, I will get e to the power minus j 2 omega and plus 2 omega. So, that will be twice cosine 2 omega. Similarly, h2 e to the power minus j 3 omega into twice cosine omega plus h3 e to the power minus j 3 omega. Okay. If I take e to the power minus j 3 omega common, I find inside it will be even 2 can be taken out. Okay, 2 need not be taken out. Twice h naught cosine 3 omega plus twice h1 cosine 2 omega plus twice h2 cosine omega plus h3. Okay. So, these are all real quantities. There is an e to the power j theta term. So, directly you get the phase as 3 omega. Phase is varying linearly with omega. Is that all right? So, phase is minus 3 omega. The magnitude is changing. Can we generalize this? If n is, we have taken odd, therefore, h e to the power j omega summation will be e to the power minus j n odd. We had 7 points, is that so? So, n minus 1 by 2, it was half that angle, half that value, half of 6, is it not? So, n minus 1 by 2 into omega, is that all right? Then h3 is h n minus 1 by 2, that is a free floating term, plus 2 times sigma, I can write h k. If this is k, then this is 3 omega. If this is 1, this is 2, this is 2, this is 1. So, coefficient of that will be cosine of n minus 1 by 2 into minus k into omega. Is that all right? K varying from 0 to, this will be less than 1. So, n minus 3 by 2. Is that all right? Let us now go for n even. Then we have, say, n is equal to 8. So, H0, H1, okay, H2, H3, H4, H5, H6 and H7. So, H1 is equal to H7, H1 is equal to H6, H0 is equal to H7, H1 is equal to H6, H2 is equal to H5, H3 is equal to H4. All right. So, this is equal to H3, this is equal to H2, this is equal to H1 and this is equal to H0. Then what will be H e to the power j omega, like this and this, if you pair, it will be H0 plus H7 e to the power minus j 7 omega, and H7 is nothing but H0, all right, plus H1 into e to the power minus j omega plus e to the power minus j 6 omega, okay, plus H2 into e to the power minus j 2 omega plus e to the power minus j 5 omega, plus H3 into e to the power minus j 3 omega plus e to the power minus j 4 omega. Is that all right? Now, average of these two parts 7 and 0. So, 3.2, 3.5, 3.5. So, I take 3.5 omega e to the power minus j 3.5 omega common. So, e to the power minus j 3.5 omega, I should write 7 by 2, no? Okay, we will see later, that would have been better. Now, I will get twice H naught cosine 3.5 omega plus, now I can take 2 outside, no, all of them are paired. So, H1 cosine 2.5 omega plus H2 cosine 1.5 omega plus H3 cosine 0.5 omega. So, in a more general form, if I write, it will be e to the power minus j, I have taken n even. So, 8 minus 1 7 by 2. So, it is n minus 1 by 2 omega common, okay. Then 2 into sigma h k, if I write, k varying from 0 to 3, that means n by 2 minus 1. Is that all right? N by 2, 8 by 4, 8 by 2, 4 minus 1, 3. H k cosine, how much is it? 3.5 means n by n minus 1 by 2 minus k into omega. Is that all right? So, this is for n even. So, n even and n odd, they will be differing in the general expression, not in this is same, phase is same, n minus 1 by 2. Now, it will be 3.5 omega, earlier it was 3 omega for 7 point sequence, for 8 point sequence it is 3.5 omega, and inside this term was free, these terms were like this. Now, here it is identical, you see hk cosine n minus 1 by 2 minus k omega, only this term was earlier present, now it is missing, all right. Now, let us have another symmetry, this is antisymmetry. An antisymmetric sequence is like this. Once again, let us take n is equal to even first, okay, even. So, this is H0, say this is H1, H2, let me take only 3 points, 3 points on this side, 3 points on that side, say 6. Then we have H2, H3 is minus H2, then H4 is minus of H1, and H5 is minus of H0. All right. Therefore, Hz or H e to the power j omega will appear like this: H0 plus H1 e to the power minus j omega. I have arbitrarily taken plus and minus symbols for H1, H2, but whatever is the value of H1, it will be negative of that in case of H4. Whatever is the value of H2, it will be negative in case of H3. So, H2 e to the power minus j 2 omega minus H2 e to the power minus j 3 omega minus H1 e to the power minus j 4 omega minus H0 e to the power minus j 6 omega. Is that all right? 5 omega, 5 omega. Now, if you pair them, what do you get? Equal to H0, okay, into 1 minus e to the power minus j 5 omega plus H1 into e to the power minus j omega minus e to the power minus j 4 omega, correct me if I am wrong, H2 e to the power minus j 2 omega minus e to the power minus j 3 omega. Okay. So, once again you take the averages, this is 5, this is 0, this is 4, this is 1. So, 5 by 2 is the common. So, H0, okay, I will take e to the power minus j 5 by 2 omega common. Then what do you get inside? You get 2 H naught sin 5 omega by 2 with a j term. Everywhere there will be a j term because it is minus. So, I will put j term, also they are paired. So, 2, I can write like this, 2j outside. So, I will get H naught sin 5 omega by 2 plus H1 sin 3 omega by 2 plus H 2 how much sine omega by 2. Is it all right? So, one may write 2j, j I can always put as e to the power j pi by 2, is it not? J I can always write as e to the power j pi by 2. So, 2 into e to the power j pi by 2 minus 5 by 2 omega. Is that all right? And inside I will have this quantity. Again this is a real quantity. So, this is the magnitude and this is the phase. So, how much is the phase? Pi by 2 minus 5 by 2 omega. So, in the earlier case I was getting a phase shift like this, all right. Now, I am getting this was phase shifted by pi by 2, but again linearly falling. This was in the previous case when there is a symmetry, and this is when there is an anti-symmetry, and there are sine terms. In that case it was cosine terms. So, this is also a linear characteristics, all right. If you have some phase, fixed phase removed, then this is as good as this. What will be the general term for this? H e to the power j omega will be, when n is even, it is 2 e to the power j pi by 2 minus, this is 5 by 2, that means 6 points were there. So, n minus 1 by 2, all right, into omega summation. Now, h0, so hk, and then sine, this is decreasing gradually. So, this is n minus 1 by 2 minus k into omega, all right. What is the range of k? K equal to 0 to 0, 1, 2. So, n by 2 minus 2, okay, minus 1, all right. So, this will be the general expression. What about the antisymmetric sequence when n is odd? Antisymmetric. So, let us have again hz, okay, h e to the power j omega, I will straight away write in this form, say h0, let us take 5 terms or maybe 7 terms. So, h0 plus h, if I take n odd, it will come at say 6, including h0, there are 7 terms, say n is equal to 7, then h0 plus h6 into, okay, h0 plus h6 e to the power minus j6 omega. H6 is minus h0, that I will substitute later, plus h1 plus h5 e to the power minus j5 omega e to the power minus j omega. Thank you. Then h2 e to the power minus j2 omega plus h4 e to the power minus j4 omega plus h3 e to the power minus j, then what will be h3? It will be 0, antisymmetric. H3 cannot be equal to minus h3. So, h3 has to be necessarily 0. So, this is what I was expecting you to answer. H3, there is a midpoint which is 0. What will it look like? The sequence looks like this. Suppose this is H0, 1, 2, 3, 4, 5, 6, all right. So, at H6 it will be all right. Suppose H1 is like this, then H5 will be like this, minus of H1, and then this one is say only this much, H2, this one will be H4 is equal to minus H2. Okay. Had it been some value here, then from the other side also it would have been the negative of it. So, it cannot be anything other than 0, all right. So, here it is 0. So, what will be the sequence sum now? H1 and this is minus H1. So, I can take H1 common and again it is minus, that will generate sign terms. So, if you permit me to write, it will be twice j e to the power minus j. Now, if n is odd, 1 and 5, 6 by 2. So, that will be 3. So, minus 3 omega will be H1 H0 sin 3 omega plus H1 sin 2 omega plus H2 sin omega, all right. So, the general term will be 2, again j you can push as pi by 2. So, e to the power j pi by 2 minus 3 omega. So, 3 I will write as n minus 1 by 2. Okay. So, 2 into e to the power j pi by 2 minus n minus 1 by 2 omega. Okay. Is that all right? Inside you will have a summation hk sin n minus 1 by 2 omega minus k into omega, k varying from 0 to n minus 3 by 2. Why n minus 3 by 2? H3 is 0, all right. So, we have seen different types of filter functions. One is with a pole with a 0 either on the real axis, negative real axis or positive real axis, or if both poles and zeros are present. And then we have also seen if there are complex roots, complex poles and complex zeros, then the nature of the function can be identified either as a low pass, high pass, band pass and so on. Now, we have seen symmetric distribution, different types of symmetric distribution and antisymmetric distribution if the length is odd or even. So, there are 4 possible cases: n is equal to odd, n is equal to even, symmetric and antisymmetric. Now, FIR filters are basically functions of this type, where you have H0 plus H1 z inverse plus H2 z to the power minus 2 and so on, some Hn z to the power minus n. Say this is the type of filter coefficients that you want to find out. Suppose I ask you to design a filter having linear phase characteristics, then these coefficients will have symmetry We have just now seen if there is a symmetry, there is a linear phase characteristics, and if I give you the gain function, you can calculate what will be the h, the coefficients. Once you know h, h0, h1, h2, all the h values, say it is an 11 point sequence I want, then you can design it from the specifications, and the filter design is very simple. The filter is going to meet all the requirements. Now, what is the specification, nature of specification that we give? We normally give h j omega function. Suppose it is a low pass filter. There are various types of specifications given. Somebody may give a monotonically falling low pass function. Somebody may define this alpha, the 3 dB cutoff point is so much, and roll off, how fast it should fall, the transition is given. All right. Somebody may give within this frequency band, within this tolerance, it should come at such and such frequency. At omega 1, it should come within a certain dB level. All right. There can be also specification like this. There can be a tolerance in the pass band where we define a pass band, and so on. There can be various types of specifications. Now, if you know h omega, h e to the power j omega, magnitude function, if you are asked to design a linear phase filter, then we will take up only the magnitude function first, then try to see how the linear phase can be obtained. There are various approaches. The first one is Fourier series approach. Fourier series. All right. The next one is discrete Fourier transform, DFT approach, for which we take the help of FFT algorithms, which is very fast. All right. And then there are many computer aided design, we will take up those also, computer aided design approach. There are many variations of this that we will see later on. So, I will just give a brief introduction to Fourier series approach for the design of an FIR filter. You know, h omega that we are considering, I am in the habit of writing only omega. So, quite often I am slipping that. It should be always written e to the power j omega to distinguish it from the analog domain. Suppose this is a filter function. This is our pi by 2 pi. This is kept normally well within the band, is kept within pi. It will be repeating, is it not? It is not exactly. This is pi. Suppose I define this function, I give you some analytical form, all right. Then h omega, whatever be that function, if this is given, multiplied by e to the power j omega and d omega from minus pi to plus pi, all right, will give me into 1 by 2 pi, will give me h n. Is it all right? N will correspond to this n, is it not? So, this is basically reverse transform. We are taking I dTFT. Because it is periodic, so you will get a sequence Hn which is of infinite length. So, you will get an infinite series. For Hn, then truncate it at a suitable place. Next step will be truncate it at a suitable length. So, suppose by doing this you get a sequence of H0, H1, H2 like this. Hn by integrating from minus n to plus n, it will be symmetric? You cannot say. Okay. Let us see what it will be like. Suppose we take a very simple function like this. It is already defined here also, because it will be a mirror image. So, minus pi to plus pi, and this is the cutoff omega c minus omega c. I am taking h equal to 1 normalized value and a very simple low pass filter. What will be Hn? It will be 1 by 2 pi minus, this is 0. So, I can take minus omega c to plus omega c, 1 into e to the power j omega n d omega. How much is that? 1 by 2 pi e to the power j omega n. So, it will be e to the power j omega c n minus e to the power minus j n omega c divided by j n is equal to 1 by 2 pi. This minus this will give me 2 j sin omega c. So, j will get cancelled. So, 2 sin omega c into n divided by n. Okay. So, how much is it? 1 by pi sin n omega c by n. I can include omega c, sin n omega c by n omega c, and I can multiply by omega c. This is a multiplier. So, what is this? It is a sinc function. So, Hn will be these values. The sinc function looks like this, these values. If I would have considered h minus n, then I would have got these values. Okay. So, if I now truncate say at the 10th term, this is h0, h1, h2, h3, h4, h5 and 10th term. I take h minus 1 as h plus 1, h minus 2 as h plus 2 and so on. Okay. And then give it a shift by 10 steps, then what do I get? A 21 point sequence. First middle one is h0 and then there are 10 terms after this. There are 10 terms before this, I am considering them and then give it a shift. What does it look like? Symmetric function which will ensure a linear phase. Is that all right? So, what you need to determine is only the first 11 coefficients including h0, another 10 coefficients, all right, and then you can generate a sequence with a shifting. I will call it h0 dashed which is equal to minus h10, h1 dashed which is equal to minus h9 and so on. So, I will get a sequence of 21 points. So, it is a 21 point sequence filter which will ensure that this is more or less approaching this. If you have a larger length, then it will be coming closer to this, that means the error will be less. Okay. Okay, I think we will stop here for today. Thank you very much. So, we will take up from this in the next class. If you have any questions, please bring them in the next class. All right.